Hi geographers, and welcome to the second video on the topic of the tectonic hazards. Today's lesson's on the Earth structure and plate boundaries. All you need for today's lesson is a piece of paper and a pen. If you'd like to pause the lesson now just to do the do now and write your title, that would be great. Right, so let's go through the answers to the do now. Question 1, a natural event such as an earthquake becomes a hazard when it affects people. Number 2 is 100 pupils. A challenge in Charles Dickens' ward is 32% of people leave school with no GCSEs. Lagos is internationally important because it's home to many TNCs such as Microsoft. Number 5 is 600 million spent by tourists in Portsmouth, and urbanisation will increase the risk of natural hazards as more people will be living in an area. So if one building collapses into another, the chance of death will increase. So let's crack on with what we're doing today. There it goes. So we've got some keywords today. We've got Pangaea, which is the name of a supercontinent believed to have broken up into the existing continents we have today. Plate boundary / margin, that is an interchangeable term, and it's just where two tectonic plates meet. The term tectonic plates, this is pieces of the Earth's crust, and convection currents, movements of hot magma rising, spreading and cooling within the mantle. And if you look at the bottom left, you can see the blue zone, so the independent task you're going to finish on today, which is suggest how the process is taking place at different types of plate margin can lead to earthquakes and volcanic activity. Right, so we continue. What we can see here first is the world map as it is today. And if we look at the world map, we can see that the continents are in their places. And with that, we can see that if we look at South America and Africa, we can start to see that the east coast of South America looks like it fits into the west coast of Africa. And that's because if we look back millions of years, Earth was connected. All of the continents were joined together, and this was known as Pangaea. And what happened over millions and millions of years, continental drift took place, and that is where the tectonic plates have moved apart from one another, and therefore so have the continents. So if we look here, we can see that all the tectonic plates were once joined and then slowly, due to continental drift, have moved apart. And we need to know evidence of this. So one piece of evidence is the jigsaw puzzle, the idea that the east coast of South America fits in to the west coast of Africa. In addition, we can see here at this figure 2, other evidence that the supercontinent Pangaea existed. If we look, we can see that we've got fossil evidence. So this fossil evidence shows us that a land reptile, the Lystrosaurus, has got fossil remains found in Africa, India and Antarctica. As we know today on the world map, those three continents are all separated by large oceans. This proves that the land must have been joined for the fossils of a land-based reptile to be there. Likewise, we've got fossil remains of plants found in Australia, Antarctica, India, Africa and South America. So by using these fossils as evidence of land-based reptiles, we can see that the continents were once joined together as a supercontinent known as Pangaea. What I'd like to do is just pause the video here and answer the question we've got using figure 2. How do we know Africa and Antarctica were once joined? So I'll give you a moment to pause the video and have a go at answering that. Right, so answers. We could see that figure 2 shows the fossil remains of Triassic land reptiles have been found in both Africa and Antarctica. This shows that the continents were once joined, as today the climates are different due to their different locations. Similar animals would not have been able to survive in both locations. So that's the first bit done, the idea that the continents used to be joined together as Pangaea, continental drift has taken place, and the continents have moved apart from one another. Evidence to support this: fossils being found in Africa and Antarctica of land-based reptiles, and the jigsaw fit of the east coast of South America and west coast of Africa fitting together like a jigsaw. So, Earth. Earth is structured with layers, like ogres in Shrek. Earth has got 4 layers. It's got the crust, which is the outside layer of Earth, and that's the thinnest layer where we live, which is made up of tectonic plates. Beneath the crust is the mantle. This is made up of magma and is the thickest layer of Earth. We then have the outer core, which is a liquid iron nickel, and then we have the inner core, which is a solid iron nickel, and this is the hottest part of the Earth. Okay. Bam, bam, bam. And then we come to look at the tectonic plates. So this is the crust. Earth's crust is split into 2 types. We've got continental crust, which carries continent, and oceanic crust, which carries the oceans. And these tectonic plates that are on the crust, this rock, is constantly moving. Okay, and it's moving due to convection currents. So a bit more on that in a moment. Okay, but it's really crucial that we understand the Earth's crust is made up of tectonic plates, and there are 2 types. The oceanic, which is denser, and the continental, which cannot be destroyed. So, there are differences between oceanic and continental crust. I suggest you write these down for your notes. So, the oceanic crust is denser than the continental crust. Oceanic crust can be destroyed, and continental cannot be destroyed. So, when we think about our plate margins, we'll see in a moment, when the 2 plates collide, the oceanic is always destroyed because it is denser. So, understanding this next image is crucial to understanding why the tectonic plates, which is the crust, move. These are convection currents, and what we have are these convection currents which are found here in the mantle. Okay, in the mantle, temperatures are really, really hot, and what happens is the warm magma rises up through the mantle. The magma then hits the crust where the cursor is now, but it cannot go through the crust because the crust is thick rock. So the magma sticks to the crust and it pulls to the side, and as it pulls to the side, it slowly moves the tectonic plate. The magma then cools down and sinks back into the mantle, where it warms up again as it gets further towards the core. As it warms up, it rises again, and the magma rises, it sticks to the tectonic plate and pulls, and that moves the tectonic plate. And these are known as convection currents. So we can see the one that I've been doing, the convection current, is going to drag the tectonic plate to the right, whereas this one on the left, when the magma rises, it sticks to the tectonic plate and it's going to drag the tectonic plate to the left. These convection currents explain why Earth's tectonic plates are moving. And as the tectonic plates move, they meet at different tectonic plate boundaries. Okay, let's have a quick look at a world map. Here's a world map. I'm going to show you 3 images. This world map shows green dots. The green dots represent earthquakes. Here's another world map. These green triangles represent volcanoes, earthquakes, and volcanoes. And here's the next world map, which shows tectonic plate boundaries, so where 2 tectonic plates meet. And when we put it all together, we can see this, that the earthquakes and the volcanoes happen along plate margins. So, let's skip one. Let's have a look at the plate margins there are. So we've got a destructive plate margin. As you can see in the animation, one tectonic plate is moving and is subducted beneath another tectonic plate. What I want you to do is draw the diagrams and label the diagrams with me as I go through them on the next example. So here we go. We have got number 1, convection currents move 2 tectonic plates towards one another. One of them is oceanic, the other is continental. As the oceanic plate is denser and the continental plate cannot be destroyed, the oceanic plate is forced under the continental into the subduction zone. As the tectonic plate subducts around here, the oceanic plate gets stuck friction builds up and this releases tremors known as earthquakes. Okay. In the subduction zone, the oceanic crust melts and it forms a magma chamber as the crust literally melts into magma. And we get a large magma chamber forming beneath the continental crust. Due to increased pressure in this magma chamber, where the cursor is, so increased pressure in the magma chamber, the magma is going to erupt upwards through the continental crust, and this is going to have really sticky lava and form a steep-sided composite volcano. The next plate margin is a conservative plate margin. If you look at the images here, we can see two tectonic plates sliding past each other. An example is the Pacific plate and North American plate are sliding past each other at different speeds. Again, what we need to do is draw the diagram and label it as we do on the next photo. So, as you can see here, the two tectonic plates are sliding. Step 1. Convection currents in the mantle cause the plates to move. Step 2. The two plates slide past one another and stick. As the plates get stuck, pressure builds up. That's because the convection currents are still trying to move the plates, but they can't because they're stuck. As this pressure builds, there's eventually a slip, and as there's a slip, pressure is released through seismic waves in the form of an earthquake. At a conservative plate margin, we do not get any volcanoes. And finally, we get a constructive plate margin. If you look at the image here, we can see the tectonic plates are moving away from one another. An example is the Mid-Atlantic Ridge in the Atlantic, where the North American plate and Eurasian plate pull apart from one and other. So again, copy the diagram and label as we go. So step 1, the convection currents in the mantle pull the plates apart. As the plates are moving apart, this can lead to small tremors known as earthquakes. Step 2. A gap is created in the crust. And what's going to happen, we can't just have a gap on the crust leading down to the mantle. So within the mantle, magma rises and runny lava slowly seeps out of the gap. This runny lava will eventually cool, solidify and turn to new crust and new rock, and this explains how the country of Iceland has formed. And also, as this runny lava solidifies, it travels quite a long way and it forms gently sloping, shielded volcanoes. So those are the three types of plate margin. What I want you to practice is this exam question. It says, suggest how the processes taking place at different plate margins can lead to earthquakes and volcanic activity. And we've got figure 6, which shows us three different plate margins. Paragraph 1 is going to be on a constructive plate margin, how we get earthquakes and volcanoes. Paragraph 2 is going to be on a destructive plate margin, how you get earthquakes and volcanoes. And paragraph 3 is going to be on a conservative plate margin, how we get earthquakes. So we'll just break the question down. Okay, so if we look at this, we're talking about processes at different types of plate margin can lead to earthquakes and volcanoes. Okay, remember, step 1 for any plate margin, it's going to be convection currents move the plate. I'm not going to write anymore because that is really difficult. So think of the question as a list. You're going to start with convection currents move the plate and then just explain what is happening at each tectonic plate margin and how that leads to earthquakes. If you'd like to pause the video here, I'll give you time to complete the question. Please use your notes if you are stuck. Right, perfect. So, just to finish off, what we can see here, this is a perfect answer. So we've got the figure shows a constructive plate margin. Here, convection currents in the mantle move tectonic plates away from each other. the movement can cause small earthquakes. As the plates move apart, it creates a gap in the crust. Magma from the mantle rises to fill the gap. The magma cools and turns to solid on the Earth's surface, forming gently sloping shield volcanoes. The figure shows a destructive plate margin, where convection currents in the mantle move two tectonic plates together. The denser oceanic plate is forced beneath the continental plate. This creates friction, which leads to earthquakes taking place. As the oceanic plate is subducted further into the mantle, it melts into magma, forming a magma chamber. Pressure builds up in here, and the magma eventually erupts through the continental plate, creating a steep-sided volcano. And then finally, the figure shows a conservative plate margin, where convection currents in the mantle move two tectonic plates past each other. The plates get stuck as they move, which creates friction. This is released through seismic waves, which cause earthquakes. So, if you answered the question and you now see mine and be like, oh, I might have done it wrong, the final slide here allows you to have another practice. Okay, so you've got the same question, 3 paragraphs, some keywords. Thank you for watching. Please remember to like and subscribe to CVA Geography to stay up to date with any more videos helping you with your GCSEs. Thank you. Bye.